Yeah, thank you, Pradeep, and good morning to you all. And once again, congrats, Amrita, for this wonderful recognition. Prof. Amrita is currently working as Associate Professor in our department, the Metallurgical Engineering Materials Science Department, where she joined in December 2017. The main thrust of her research group is to employ different ab initio techniques to predict physical properties of solid-state materials, whereby she also uses machine learning to analyze material properties for their quantitative applications. She has been elected as a member of National Academy of Science, India in 2020. She has already received several external research grants in the form of DST, Inspire Faculty Award, Early Career Research Award, BRNS Regular Grant, etc. So let's welcome Prof. Amrita, please. Prof. Amrita.
Yeah, am I audible?
Yes, please, go ahead.
And my screen is also visible, right?
Yes, yes, yeah.
Okay, thank you, Professor Narsimhan, for such a warm welcome. So, and I thank IRCC for recognizing me with this particular award. So, I will show you some of the work that we have been doing in the last 4 years. So, in the last 4 years, I have been working on developing some of the machine learning methods and applying them for finding some of the physical properties of solid. So in this particular work, I'm going to focus only on one of the particular application that we have strongly doing in the last 4 years. However, the group also focuses on various other fields. So we work in computational material science. So thank you, Achinta, for already introducing the field. So I need not to introduce it further. So Achinta works in this particular length and time scale, which is like of the order of femtosecond, and materials phenomena of the order of in the length scale of 10 to the power minus 9. But I generally work in this particular area. So it's a little bit higher than quantum chemist. So we do not look in so much of accuracy, but we try to but we keep the accuracy into mind and then try to predict phenomena, materials phenomena at a little bit higher length and time scale, which is in this. So what we use is generally density functional theory. And I will just therefore, briefly, introduce density functional theory because Achinta has already, introduced it, and therefore we'll go ahead. So in principle, if you're solving a quantum mechanical problem, what you need to solve accurately is an electron ion problem. And in our system, like if it is such kind of complex system that you see in here, then there would be a lot of electrons and a lot of ions. So if the number of electrons and ions goes really to a order of 100, 200, and maybe even more than that, then it's really problematic for solving it accurately. So therefore, you cannot solve it accurately. You have to go for some approximations. And one of the particular approximations which has done avidly very well in the last few decades is density functional theory. So whereby if I give you a layman's picture, so you have the same electron ion problem, but you kind of consider an effective potential and you solve a single particle equation in an effective potential. That helps us enormously. You do not have to store so many wave functions, first thing. The second thing is also you can save a lot of computational time. And because of that, nowadays, the supercomputers can give you very good kind of estimation of the materials phenomena already before you are synthesizing them or studying them in laboratory. So thus DFT has its own advantages and also some of the disadvantages. But the advantages are like you can predict materials properties, you can predict structure, you can predict a lot of new materials and so many other things. So therefore we are going forward. So in the last few years I have worked on the field of charge and heat transport. So I will briefly introduce the problem over here. So thermoelectrics as a material. So here the thermoelectrics phenomena of thermoelectrics is schematically shown. You can see that in this particular solid, one of the end is kept as hot and another as cold. And therefore you have efficiency, but the efficiency is not as good as like, you can generate a voltage by keeping these two ends into different temperature. But the efficiency is largely compromised. It's not as good as a Carnot engine efficiency. And it is compromised because of the presence of this factor ZT. And you can see, like, if I plot efficiency as a function of ZT, then in order to recover any meaningful, efficiency, you need to have a ZT beyond 4 or anything. But this is a very non-trivial problem, because if you try to get or maximize this particular quantity, A square sigma, which are the power factor, which is the Seebeck and electrical conductivity, then you also get, this particular KEL in the denominator, which shows a similar proportionality with the sigma EL. On the other hand, you can tune this lattice thermal conductivity, which comes also in the denominator, to some extent independently, and we generally, focus on this particular, tuning of this particular, transport coefficient while we are working. And therefore, like, we can still somehow tune and get a reasonable ZT that I am going to, discuss right now. So how density functional theory can help? So we can perform a large scale, high throughput calculation, where we are not treating any of the solid very differently, but we do large scale quantum chemical, simulation, and then we figure out, like, what are the, best thing about one particular solid. So one can, check for their thermodynamic stability. They can check for band engineering. So by band engineering, what I mean, I will again discuss very briefly schematically. And then one can look into the transport properties, and then may go ahead to predict efficient thermoelectrics, right? So in this case, we are showing only the band engineering concept, where we are looking into the electronic structure. So this is a schematic, situation shown for a fictitious solid. So you can think, like, there are a lot of degeneracies in the bands, in the conduction band. And in principle, all the thermoelectric materials are doped. So if this particular materials is N-type doped, and there is a doping limit of this, and you're coming here, then you can see so many bands are converging. So if such kind of situation can be inflicted in a material, somehow by doping or substitution of the compounds, substitution of the compound, then that's a very tremendously good situation to look at. Similarly for the p-type situation, I'm not going into the details of this schematic. So keeping as one particular case in mind, so these are the Heusler materials, and we tried to substitute this Heusler material, and we wanted to compositionally tune the entire space, starting with 3 different elemental rows in mind. So these 3 ideally gives a 18 valence electron count half Heusler. It's very stable. So therefore we can look into and find what is the exact compositional space we should look, or one should look, if they are going ahead and tailoring the thermoelectric properties. So we further proceeded and performed some density functional theory calculations. In principle, we calculated all these properties, which we are not showing into details. But here you can see, like, this is just to show. I'm not going to overburden you with the electronic structure in here. So in 2 situations, so this, after we have tailored all the properties, we find, like, if you are doing an X site substitution in this material, so these materials are XYZ materials, if you're substituting it at the X site, it's not, it's very good. On the other hand, if you're also doing a Z site substitution, it's also very good, because it retains the valley degeneracies, as you see at the conduction band. However, if you are doing a substitution at the Y site, it's not very good, and it breaks the entire symmetry of the lattice. And that is the reason that all the literature until now in thermoelectrics focuses on either X site substitution and Z site substitution of Heusler materials, but not Y site substitution, because it kills the electronic structure. So it kills the degeneracy in the electronic structure. So therefore we proceeded further, and we showed, like, yeah, that is true. So the Y site substitution is not good, but the X and Z sites are. And therefore, like, what should one do? So if you also look into the lattice thermal conductivity, it is quite lowered in these materials, but that's not the only thing that can be done in this type of materials. So in principle, the Y site substitution is also good if they are limited to a very little bit amount of Y site substitution, because that will drastically lower the lattice thermal conductivity, which has been shown in this figure. So where Y site substitution has been done and the lattice thermal conductivity has been lowered. And that also very drastically, because the electronic part is not changing. So we studied this phenomena in more details. And first time, when we did it for the first time, we did it with one particular compound, which was zirconium nickel tin with a little bit Y site substitution. And we found like there are some rattling modes of nickel at very small, doping concentration, which kind of, do not appear as soon as the amount of nickel concentration in the system is more. So therefore, what we did is like we kind of, tried to see like whether this is a phenomena across all the half Hoysler's or not. So therefore, we took into account of different compositional space, keeping the 18 valence electron count in mind. And we saw that indeed, in most of these materials, like this is the full Heusler compounds having lattice thermal conductivity as high as 10 to 20 at least. So, but the moment there is a little bit of substitution at this Y site, then the lattice thermal conductivity drops drastically. And these are very accurate calculation taking into account of all the anharmonic effects and everything possible. So we proceed further to look what is going on, and we could show a phenomena where if you are limiting to very small percentage of self-side doping in the Y side, then and if the generally this lattice, so this is the extra atom peak which is shown in here. These are the rattling modes. If the rattling modes come within the acoustic region, then there would be a heavy disruption of the scattering phonon scattering lifetime. And you can see like the phonon scattering lifetimes are highly disrupted. However, if you have a kind of doping where due to the frequency this goes into this type of region without hampering the acoustic mode, then you will see like this type of situation is not like too much good, because the lattice like the phonons are, the scattering lifetimes are disrupting the phonos, but not as much. So we proceed further. So here we show a conjecture. So in principle, what is the problem in this type of calculation is each of this calculation is too much, like it takes too much of cost, computational cost, and you cannot calculate them very accurately. So therefore, like what we thought is like instead of calculating each of these phonon calculations one by one explicitly for each of the system, why do not we make a method based on machine learning? Use machine learning to calculate the lattice thermal conductivity. In that case, like we do not have to do this painful, lengthy calculations each time we do. So therefore, we propose a machine learning model. We proposed a machine learning model. For I will just briefly, introduce that. So in this case, we first have to have some of the calculations which have been done. Either calculations or experimental results, both can be done. In this case, our case is the first principles calculation which we have performed for as many as systems as possible. And then once we build the model, then depending upon the model, we can predict the lattice thermal conductivity of many other materials which falls into the same class. So I will show you very briefly. So we took about 150 sample points where the phonon calculations have been performed accurately, and third order phonon calculations have performed to calculate the lattice thermal conductivity from first principles. And then like these are the different features for each of the elements. There would be a lot of features. Then the compound, entire compound, you will have to have a lot of features. And similarly for the thermal properties also, you will have to have a lot of compound features. So those you calculate, those you generate. So we have calculated and generated the complete descriptor space. With about 150 descriptors we start, and then like we do a systematic analysis to get rid of some of the descriptors at regular interval. How we do that, we are not going into the details of this. But once we do this, what we showed is that like the elemental features that you see in here, so these are for the elemental features, which are the features pertaining to an element, not a compound, or not a thermal property of a compound. So this gives as good as accuracy as a complete feature list, which is shown in this here. So therefore, what we proposed is like you can perform very accurate calculations, or you can predict with the elemental subset the lattice thermal conductivity of a given material. And you can see the accuracy is not too very bad. So we further do a complex sensing type of we apply compressed sensing. What does this particular method do? Is like now suppose my last feature list is about 26 features, but I want to combine it to a very complex feature list and find like whether I can achieve the same accuracy or not. So then you do compressed sensing and you figure out in which complex dimension we can have a lattice thermal conductivity calculated. So this is how we have this is the output of the compressed sensing that we have applied. And you can see this is the lattice thermal conductivity. And this is like only the distance between X and Y atom. This is a compound feature, but it can be also done for elementals, which is shown in here. So you can see the lattice thermal conductivity is following almost a like linear kind of trend in here in both cases. So anyway, so we proceed further. So and while doing that, here the after compressed sensing, the number of dimension is reduced to only 7, and you can still see like we get a very accurate model for the test data as well. So therefore, what the conjecture is like this is shown for only the lattice thermal conductivity, but one can also take into account of all the different degeneracies, all the valley degeneracies, all the effective mass of electronic in the electronic structure, and can build a similar model for power factor. And similarly, with all this type of inputs, one can predict very good thermoelectrics while doing all the computer simulations. So this is very good. So far, so good. Some of the but last but not the least, one has to realize them in the experimentally in the laboratory. So which is also like in our future scope, which we are keeping an eye at. So these are the different areas that we work: thermoelectrics, defects in semiconductor, and spintronic materials. This we are currently working on, and then like I thank my group. So this the works that I have shown you primarily is done by Parul. So she is my final year PhD student, and also to some extent the machine learning work has been done by my student Dipanita. But like I should mention that all my students are equally important to me, and they have helped tremendously in getting the group growing. So I thank now finally all the funding agencies. So they have funded us generously. So I have no complaints against the funding that I have received until now. So I thank IRCC for giving me extended seed grant. Even though I'm a theoretician, I'm trying my efforts to do like experiments as well. And IRCC has shown their trust on me. So I thank the MEMS department for helping me magnificently for building my group, and IIT Bombay for showing all the trust in me as a researcher, theoretician, and experimentalist. Thank you very much.